can see the canvas.
Okay,
Yeah.
good. So everyone's seen this, and so we have essentially 7 teams. 2 of them are section 90. So there's a daylighting photovoltaics teams, and those teams will be presenting, submitting video presentations. Whereas the other 5 teams will be doing live Zoom presentations in class, as we discussed before. So first things first, assignment 1 is make sure you contact your teammates and create a team name and a plan for remote work during the rest of the semester. So make sure you do that. And that's what I called assignment 1, and that's due next Monday. Next September 8th, so next Tuesday. Okay, let's go quickly to the schedule. So today, by the way, all the lectures are posted here as well, as well as on Canvas. So hopefully everyone's able to access it, the videos.
Yeah, I also updated everything on Canvas.
Great, thanks, Apratham. So today we're gonna jump into geometrical optics, and Apratham gonna lead this lecture. So one quick comment I wanted to make is that everything that we will learn until the midterm, which is October 15th, so the reviews on the 13th, will be included in the midterm exam. So make sure you are aware of that. So everything from last week till October 13th, which is the review, will be included in the exam. So pay attention. Let's see. Okay, the assignment 1 is due next Tuesday, and the assignment 2 is due September 15th, a week after that. So keep in mind, I'll give pretty clear instructions for assignment. There are some preliminary instructions here that you can access. I'll give more detailed instructions, updated instructions by Thursday for assignment 2. Okay. Okay, if there are no other questions, I'm gonna stop my share. And first of all, are there any questions regarding the teams, projects, what you need to do? Okay, everyone's clear. Great. I'm gonna make Apratham the host. Let's see. Host. Apratham, you should have control now. So feel free to share your screen. I'll be online as well. I'll monitor the chats. So again, if you have any questions, just post on the chat, or of course you can also talk, but chat might be easier.
Hello, sorry, I think I was muted. So can you see my screen?
Not yet. I think you need,
no?
Oh.
Really?
Okay, everyone else can, I can't, but that's okay.
Okay, just check something. So I'm going to go back and forth between a PDF, which has the lecture slides, and a PowerPoint presentation that I have where I did some of the math. So when I switch, can you now see the PowerPoint?
Yeah.
Yes.
Okay.
Yes.
And so this is the PDF. Okay. So in this lecture, I'm going to talk about geometrical optics. And there's a bit of math involved. So usually in the past few years, I work out the math in class. But since this time I don't have that opportunity, I'm going to try my best to solve the math step by step using some PowerPoint slides that I prepared. Okay, so let's start with the lecture. So we have a brief overview of the modern view of light. I think you are all familiar with this. And if you have any questions, you can just ask me, just shout out your questions. I'll try to make this sort of a discussion as we go along. So the photon is the elementary particle of light, and it is massless and has the speed of light. Light can also be thought of as a wave, which gives us the wave particle duality, and any wave has an energy associated with it, which is given by Planck's constant times the frequency. Can you also see my mouse cursor as I point to things? Sorry. Okay, yeah. So the momentum associated with the wave is shown by this equation. Again, so h is your Planck's constant, lambda is the wavelength of the light, and momentum is p. And finally, we have a dispersion relation which equates the speed of light with the wavelength and the frequency. So these are just some basic definitions. And now we will look into how we can use the concept of array to solve some optical systems. So the idea behind these lectures is to get you familiarized with analyzing optical systems. Suppose you have you want to make a camera or some imaging optics, and maybe it's fairly complicated. So you would want some way of solving the math and figuring out how to build your lenses and stuff to get your imaging properties correct for your system. So eventually we will see that when optics get more complicated, like suppose even our cell phone cameras have multiple lenses these days. The DSLR cameras all have multiple lens elements inside the long tube-like lens. So for those, you would eventually need to resort to some kind of a software that is going to solve the math for you. And I think in the upcoming lectures, we have sorry, 1 or 2 tutorials which will show you how to use certain softwares which can solve geometrical optics problems. But before that, we should also understand the mathematics that goes into building these softwares, right? And that's what I'm going to talk about in this lecture. So light, as we discussed in the first slide, can be thought of as a wave. And geometric optics, what it does is it approximates the wave nature of light in the form of array. So remember, if you have a wave traveling in space, it is basically a disturbance that is propagating. So I can draw out the disturbance in the form of a sinusoid. And then suppose this is at time equals 0. So the wavelength is defined as from this, suppose from a peak to a peak or a trough to a trough. You're familiar with this. And we then define a wave front as planes of constant phases. So every point on here, which is at the same phase, can be thought of as a wave front. So imagine the point which is at the peak, or which is at the trough, or at the 0 line. So all of these are in phase. So we can approximate these as wave fronts. So now if I advance the time by a very small time segment, suppose delta t, what will happen is that the disturbance will move forward, or in this case, it's going from left to right. So it'll move toward the right a little bit more. So all these points will shift, right? So you'll see all the points which were in phase sort of moved forward by an equal distance. So it is as if the wave fronts that we defined as the planes which are going through these points of same phase, the wave fronts, the parallel line, the parallel planes, they move forward or they move toward the right. So now if we trace out a line which is perpendicular and moving through these parallel wave fronts, we can call this as a ray. It basically shows you the direction in which energy is flowing when light is propagating from one point to another point in space. So if you have homogeneous medium, like there's no change in the medium properties, like suppose the light is propagating in vacuum or inside a homogeneous medium, like inside glass slab or something, light will always travel in a straight line. That's what we assume for the time being. Next, the question is what happens when light interacts with matter? So in the case of vacuum, you see that light is just undergoing rectilinear propagation. Inside some matter, some material, light will have to encounter the different atoms and molecules of the matter. So it will suffer a decrease in the speed of light. And this, the velocity which light has inside the medium, defined by V, equals the speed of light divided by the refractive index of the material. The other way of looking at refractive index is basically the scaling factor, which goes into the reduction of the speed of light inside a material, some material, when light is traveling through some material. So we can define this as the refractive index, and an example is vacuum or air has refractive index of 1. So basically that means that light is not interacting with anything and it travels at the speed of light. While glass has a refractive index of 1.5 to 1.6. Certain other materials have even higher refractive indices, and so on. So, which means that inside those materials, the light is basically slowing down. Next, we come to another term called the absorption coefficient. This tells us how much of the light energy will be lost by absorption by the material molecules. And that is defined as alpha. And the energy transmitted through a length L of the material is defined as, so this is basically the energy is transmitted is equal to exponential minus 2 alpha L. So just this is basically a scaling down of the energy. So some energy is absorbed inside the material. Example, so I just said glass has refractive index of 1.5. On the other hand, glass fiber has a very low absorption coefficient. So you can see the absorption coefficient is second place of decimal per kilometer. So see, the definition is with respect to a length L which is traveled inside the medium. So over really long distances, glass fiber has very low absorption coefficient, which is why optical fibers are made of glass and it can carry light for very long distances without suffering significant loss in the transmitted signal. Okay, so now we come to the two primary phenomenon associated with optical systems. The first one being reflection. So reflection, can think of reflection from any surfaces. Mirrors definitely come to mind. And I think we have all learned this equation in high school. So if you have an incident light defined as a ray coming in, let me see if I can see the chat, if any of you ask any questions.
No question.
Okay, yeah, I don't think I can see the chat. Yeah, but anyway,
No
if you
questions
have
right now.
questions, just shout out your questions, maybe. Yeah. So
I can monitor it up with him. It's okay.
Okay, so yeah, so if you have an incident ray of light coming in as shown over here, and the incident light is coming from a medium 1, and this line shows the interface between medium 1 and another medium, which is this medium 2. And this interface is reflective, which means most of the light will hit the surface and go back into medium 1. We can draw this ray, which I'm now pointing to, as the ray which shows the reflected light. Now we draw the normal to the interface between the two medium. And the law of reflection states that the angle subtended by the incident light with the normal, defined here as theta I, will be equal to the angle subtended by the reflected light to the normal, theta R. So simply, the angle of incidence equals the angle of reflection. Obviously, remember that in no medium is perfect, so some of the light will also get refracted into the medium. But if it's a very, very ideal reflective surface, this energy is very, very low. So, and the other law is that the normal, the incident, and the reflected rays all lie in one plane. So in this case, everything's inside the plane of the screen, basically, that we're looking at. Okay, so the second phenomenon is refraction. In this case, suppose the medium is, just a second. So suppose the medium is the first medium is air and the second medium is glass, or the second medium is water. So in this case, most of the light will enter the second medium, but it will suffer a change in direction of propagation. But again, a small amount of energy is going to get reflected back. So in the case of refraction, we define the angle of refraction as the angle between the refracted light, which is going into the second medium, with the normal, right? I think someone has trying to enter the room. Dr. Menon, can you? I should probably. Okay, I think someone got added. Yeah. Okay. So the Snell's law defines the phenomenon of refraction, which states that the N1, which is the refractive index of the incident medium or the medium from which light is incident, times the sine of the incident angle theta I equals N2, which is the refractive index of medium 2, times the angle of refraction theta T, defined as the angle between the refracted light ray and the norm. So this is Snell's law, very important, and we'll use this multiple times going forward. And again, like in reflection, the incident, the reflected and refracted rays all lie in the same plane. So just 2 points to remember. In the case of reflection, most of the light is going back into the medium from which it was coming in. And in the case of refraction, most of the light is going into the second medium. Again, in either case, a small energy is going to be, so in the case of reflection, going to be refracted, and in the case of refraction, going to be reflected. The next case is a special case of refraction, which is called the total internal reflection. So a good way to visualize what is happening is if we look at refraction taking place, and imagine if the light incident angle is increased. So suppose this ray goes more and more towards the interface. So theta I becomes larger. What will happen is theta T will also become larger. And if you keep increasing it more and more, if you keep increasing theta I more and more, what will happen is at one point, the theta T will go along the edge of the interface, which is the critical angle, and any angles of the incident angle which is greater than the critical angle, no light will be able to enter the second medium. All of the light will be reflected back. One important point to keep in mind is this can only take place if the first medium has a refractive index which is much higher than the second medium. So one example would be when light is going from glass to air. So if you have a light going in at angles which is greater than the critical angle from glass to air, it won't be able to escape from the glass, sorry, and will get completely reflected back into the glass. So this is total internal reflection. And it's the concept which is also used in optical fibers to keep light confined nicely within the glass fibers. So remember, when theta I becomes the critical angle, the refracted ray grazes the interface. So you have theta T equals 90 degrees. And any condition where the critical angle has been exceeded, all the light will be reflected back, which is called total internal reflection. Okay. There can also be a special case called the frustrated total internal reflection, where if you have three medium, so basically actually two mediums, so it's like medium one, the incident from which the light is incident, and it's going finally into another third medium which is equal to the refractive index of the first medium. And if you have a very thin medium sandwiched in between these two layers called medium 2, and this thickness has to be like really small, in the orders of a few wavelengths of the light. So the idea is that most of the light will get reflected back following total internal reflection, but some of the light energy leaks through this interface and propagates into the third medium. This is but this energy, the energy carried by this light is pretty low. and most of it is evanescent waves. But it's just an interesting phenomenon to keep in mind, I guess. Okay, so going forward, the things that we will keep in mind is that in geometrical optics, we are dealing with systems which have dimensions which are much greater than the wavelength of light. So imagine a standard mirror is like 1 or 2 inches in diameter, but the wavelength of light is in the order of nanometers, right? So the difference in scales is huge. Wave effects such as interference and diffractions will be ignored. Again, you can also work with problems which cannot ignore these situations where the structures that you're dealing with have dimensions close to that of the wavelength of light. Like when you're dealing with nanotechnology based systems, nanophotonics and stuff like that, they have features which are in the order of microns to nanometers. So in those cases, geometrical optics is not a good as approximation, and we have to resort to wave optics. But that's not the aim of this class. So we'll ignore those. But geometric optics is very useful for everyday stuff like big optical systems like telescopes, cameras, microscopes, and all these things. So it covers a wide range of devices that we come across every day. So geometric optics that way is a very powerful tool. And so it's simple and sufficient for most situations. Okay. So going forward, any questions up till here? Okay, so the Huygens principle shows how from a point source. So if you have, so imagine this is an infinitesimally small point source from which light is emanating. So how does light propagate away from this point? So the principle states that the point source will create a primary wavefront, and on each point on the surface of this primary wavefront can be thought of as a secondary point source, which itself creates another circular wavefront. So if you then draw an arc connecting all these smaller circles, what you basically get is a bigger circle, right? So, and then on each point of this dotted curve, if you again think of as a secondary point source, you can repeat this and you'll get another circle and so on. So basically in 3D, you have a sphere which is increasing in radius, carrying energy away from the point source. And in 2D, it's a circle. So each point on a wavefront acts as a secondary point source, emanating spherical waves. And after a short propagation distance, the superposition of all the smaller spherical wavelets gives rise to a larger wavefront, which is the secondary wave. And you keep repeating it, and that way you can map out how the light is propagating away from this point source. Okay. So now the question is, why are imaging systems necessary in the first place? And why did we talk about this principle? So imagine you have some objects in space and light is scattering off from that object. That's how we basically see anything, right? If light scatters off that object. So once light scatters off different points on an object, it is going to create all these different small wavelets, which basically go out in space. Now, the information is being carried, the information regarding the object, the visual information is being carried by these wavelets, but in space, they are basically jumbled up. So in space, they get all jumbled up. Now you need some system which is going to take all these jumbled rays and bring them to a point which resembles the object from which they were either scattered or emanated. Otherwise, you can basically not make sense of the information which is out there in space. And making sense of the information is basically how we see something or image something. So seeing is basically with our eyes, imaging is with a camera or a telescope and so on. So the optical system which is used to collect all the information which was sent out from the object is an imaging system. In short, it is a lens. Like our eyes have the natural lenses of our eyes work by the same principle. So all the light which is scattered from 3D objects in space around us, they are brought to a focus on our retina by the lens. And that is how we can make sense of the world around us. So imaging systems are very important. And without them, it is not possible to image anything or make sense of the information which is carried by light from objects. So looking at it in a simple manner, the lens is the main instrument for image formation. So you have a point source which is giving out these rays of light, and you want to bring all these rays back to a point which is the image of the object. How do you do that? You put an imaging system in between these two. The simplest is the lens, which is basically a region of glass with surfaces which have been shaped to facilitate this operation, right? And how is the glass going to be shaped? How are you going to prepare it? What material do you want to prepare it out of? All these is what we have to analyze using geometric optics. So suppose you want to create an imaging system, you know, okay, this is where my object is, this is where I would place the camera's sensor and create an image. So the stuff in between is what you have to solve or design your optical system. How do you do that? You do that using geometric optics, and we will see how that happens. So what happens in the case of a lens is that the curved surface makes all these rays bend at angles which are proportional to their distance from the optical axis according to Snell's law. So once a wave which was diverging is going to converge to a point, which is going to be the image of the point source. So then going forward, what we are next going to do is analyze these lenses using ray tracing. But before that, I will just switch to the PowerPoint. And I have an animation which basically summarizes. So you can see the PowerPoint now, right? Okay. So I'm going to show an animation that summarizes all these different concepts that I talked about of wavefronts and rays of light and the lens as an imaging system so that we can see this in a more visual manner. So what I have over here is space and a 2D representation. This is a 2D animation. So this is a lens. And what you'll see are these this parallel disturbance of electromagnetic waves going from left to right from this point. And I have some arrows which will mark this progression. So this, if I pause over here, what you see is this is the light wave which is going toward the lens. So remember how in this slide, when we were talking about rays, this is actually what was sort of drawn over here. You have this sinusoidal disturbance going from left to right, and all the points of equal phase, remember, if you draw planes through them and a perpendicular line through it is the ray. So in this case, you can see the color difference determines the highs and lows. So basically here, in this animation, the red is the high, blue is the low. So you can visually make out that this is a sinusoid based on the color. And what I have drawn is, I have drawn the rays which are going perpendicular through these different planes. So these arrows, these white arrows, you can think of as the rays of light. Now if I play the animation again, sorry, something. Just a second. I think, did someone ask anything in the chat? I saw a pop-up from the chat and then it vanished.
Yeah, they're asking where can I find the PowerPoint?
Oh, you mean for Canvas and all? It's not posted yet. I'll post it on the, I just prepared it sort of like I finished preparing it last night. So I'll send it to Dr. Menon. He can post it on the class website and then I'll mirror it on Canvas after the class is over. Okay, yeah, it will be shared.
Okay, thanks.
Yeah. So now going back to this animation. So if I advance the animation again, see what happens to these rays of light when they interact with the spherical surface. So they basically bend inward, and now here you can see the light ray which was going through exactly the center of the lens. There will be one tiny spot where nothing happens, and for every other point which is along the other points of the lens, the light basically bends inward, and if I propagate it further, the light focuses to a point, and then going forward again, it expands out following the same arrows. So again, here I've drawn the other arrows here. So this animation was generated using finite difference time domain analysis. So that's a pretty complicated um, mathematical approach to solving wave optics. And that is not in the scope of this class, but the animations look pretty cool, and I think they help to explain what I was trying to talk about using these line drawings. That's why I included them here. So the goal is, in this case, we will ignore these waves that were shown in this animation, but we will just work with the arrows or the rays to make our life a lot simpler for geometric optics. So the arrows signify geometric optics, and these colored waves signify wave optics. So at the end of the day, they are both doing the same thing, but it depends where you want to use what. And in this case, we will resort to the arrows for the time being. I hope that explains broadly what I was so far discussing. Any questions up till here? Okay. So let's go into analyzing how, yeah.
Apratim, a quick point. You may want to go back to the animation and point out the reflections as well.
Yeah, so I sort of just ignored them for the timing. But yeah, remember how we talked about in the case of refraction that the medium is not ideal, and some light with very low energy would be reflected back. So you can see when this animation was created in the software, I think I assumed glass for the lens, and you can see most of the energy from the color difference is going into the lens, but some energy is actually getting reflected back. So if you compare the color, and the intensity of the color determines how much intensity of light there is. So most of the light went through the lens, but some light did go back out. So yeah, so some light was reflected back. Okay, so now let's look at how we can analyze how a lens works using ray tracing. So remember, the like I said, the waves are what are work actually doing the work, but for the time being, we'll just resort to using the arrows like I was drawing inside the animation over here. So we have a point source or an object, and a rays of light is going out from the object, and you have a lens which is going to collect all the rays and bring them to a focus at a point. Basically create the image of the object. So we have different phenomenon going on one after the other. First, light rays go out from the object and travel the distance from the object to the first surface of the lens. So this we call free space propagation in air. Self-explanatory term. Then we have refraction at air glass interface. So the light rays will interact with this interface and start bending in, as shown in this animation. So suppose up till here is your free space propagation, and this is where refraction is taking place. So this is refraction at air glass interface. Then light is going to propagate inside the glass, inside the thickness of the lens. Oops. Oh, here is the chat. Okay, I just found the chats. Okay, I can also keep an eye on the chat. Yeah. So then you can see the light is propagating inside the lens. So here, so that is free space propagation inside the glass. And finally, if you have another curved surface, just for the simplicity of the animation, I didn't curve the second surface. I just kept it straight, but basically you would have another refraction at the second curved surface, and then light will propagate in free space in air again. So we have to analyze these 1, 2, 3, 4, 5 situations. But essentially, there's actually two things going on. One is free space propagation and one is refraction. The free space propagation might be in air or inside glass, but it's the same phenomenon. Only the refractive index will change. In air, it will be 1. In glass, it will be 1.5. And refraction at two interfaces is going on. So essentially, there are two phenomena that we have to study. And if we understand those, we should be able to analyze these systems. So going forward, one important thing to keep in mind is an approximation which is used in geometric optics. It's called the paraxial approximation. And paraxial approximation states that all these angles subtended by the rays in geometric optics are pretty small, which means that the rays are close to the optical axis, right? So this angle subtended by the ray, and the optical axis is, by the way, this horizontal axis. This angle epsilon is very small, which means that you can use your trigonometric approximations such as sine of that angle is that angle, tangent of that angle is that angle, and cosine is equal to 1. So all the problems that we are going to solve in this class are valid for angles which are smaller than 30 degrees, which is okay for the time to assume. So next, in paraxial approximation, what happens is if we assume these angles are very small, it means that the distance between the ray which is hitting the curved surface at this point and the ray which is hitting the curved surface at this point is also very small. So it is okay to assume, to neglect this small distance, basically. So now I'll resort to my PowerPoint again. So in the PowerPoint, we see that this is the paraxial approximation ray. So I've drawn this huge curved surface, which means that if the angle subtended is very small, this region, you can basically look at it in the form of a straight line. So this small distance can be ignored, like between where the ray hits here and here. So next, we have to keep in mind a small trigonometric identity, which is going to be very helpful in solving this math, is the relationship between the arc length and the radius. So if you have this section of arc, which is of length S, and I've drawn a radius going from the center to this point as R, and the radius subtends an angle theta with the horizontal axis, your arc length S equals R times theta. So this we also know from high school, just something that we should keep in mind. Now the interesting thing is, because I said we can ignore the small distance or the small gap because the angle is very small, the vertical height H and the curved arc S, they almost have the same lengths. So from S equals R theta in the paraxial approximation, we can say H equals S. So H equals R theta. Okay. Now going forward into analyzing how the lens works, we are going to zoom in to this small region for the next slide. So in the next slide, when I draw this is basically a zoomed in version of this region. Okay, so I have approximated the arc into this straight line because I've zoomed in here, and I have drawn my ray of light going in and so on. So now we will analyze how the light ray, what happens to it like in free space. What are the equations that govern the behavior of light traveling in free space? Okay, so yeah, so this is basically what these next slides are going to talk about. Usually this is the math that I work out, so I'll just resort to this PowerPoint for this presentation. So I have defined the ray of light using this arrow, and the ray of light is a very general ray, which means that it has a height x0 or x0 from the optical axis. And from this point, the light ray is going out at an angle alpha 0 subtended with the optical axis. So this blue line is the optical axis. and this dotted line is parallel to this, so same angle is subtended, alpha 0. So after suppose traversing a distance of d01 in air, the ray of light arrived at this point. So now its height has changed. We can see x0 has now become x1, like it has gained some height from the optical axis. However, we can see that the light ray did not change its angle because it did not interact with any different medium up till this point. So the second medium is on the right side of the vertical line, which is glass. Okay. So the second phenomenon is going to be refraction at the spherical surface, where the light ray is going to change the angle when going into the glass. It will change the angle, but its height will remain the same, because the refraction phenomenon takes place just at this point, which is on the interface between the two media. And the third phenomenon is that the light ray is going to propagate further inside the glass. So this will be similar to propagation in air, which means the angle will not change, but it will gain some height from the optical axis. So for free space propagation, angle doesn't change. It just changes the distance away from the optical axis. For refraction, the distance from optical axis remains the same, but the angle is changed. Okay. So let's analyze each of these cases one by one. So I have my outputs, which is x2 and alpha 2. So yeah, and I have my input, which is x0 and alpha 0. So I have to figure out what is the relationship between these two. I've drawn the radius from the center of the spherical surface to this point, and the length of the radius is r. Now first we will look into the free space propagation in air case. Let's analyze that case first. And for that, let's concentrate on this triangle that I have drawn over here, okay, in orange. So in this triangle, we have our tan alpha naught, tan of this angle, equals this small height h over d01, which is shown over here. Now we have to remember our paraxial approximation, which means tan of the angle becomes the angle itself. So it becomes alpha naught or alpha 0 equals h, the small height, over d01. Or we can write h equals alpha naught times d01. So this is one of our equations, okay? So again, the goal is to find a relationship between the output side and the input side. Okay, so what is the height x1? X1 is basically x0 plus h. So x0 plus h equals x0 plus h, which was alpha naught times d01 that we derived here. So this is x1 equals x0 plus alpha naught d01. Okay, so just looking at free space propagation in air case separately, this is the relationship between the small output here, which is x1, and the input, which is x0. So I have put that equation over here. This is the place where I'll save all the equations that I derived. So your x1, your x1 equals x0 plus alpha naught times d01. Now the second thing to equate are the angles. The angle is unchanged, like we saw, because it's just propagated and nothing else has happened. So alpha 1 equals alpha 0, same angle. So I'll save that over here as well as the second equation. That's done for free space propagation in air. Pretty simple. Second is the refraction at spherical surface. So now the ray has hit this spherical surface. Remember the animation from the lens, and it's going to change its angle. But its height is going to remain the same because it's the same point. Just the direction of the ray is going to bend toward the normal, bend inward, basically. So from the slide which was here for refraction, to analyze refraction, we need the incident light, the normal, and the reflected light, right? So I have drawn those over here. Suppose this is the radius and this is your curved surface, right? So the curved surface this is basically your tangent. So remember, I zoomed into the spherical surface and approximated it as a straight line, right? Vertical straight line. So this is your tangent, which means the radius would be normal to this surface. So I've extended the radius to show the normal to this point. This is your incident ray, and this is your refracted ray, right? So basically it's this same slide, just turned clockwise 90 degrees is this. Okay, so now let's see what happens. We have to define the angles. The incident angle, which means the angle subtended by the incident ray with the normal, I've defined that as θ1 over here. And the angle subtended by the refracted ray with the normal, which I've termed as θ2 over here. Okay. So we will use Snell's law for refraction at the interface of two media. Snell's law is n1 times sine θ1 equals n2 times sine θ2. So n1 basically here, this is air and glass, but in a general case, you can think of as the left side medium has refractive index n1 and right side medium has refractive index n2. Later on, you can substitute n1 for 1 and n2 for 1.5. But let's keep things general over here. So n1 times sine θ1 equals n2 times sine θ2. Now we remember our paraxial approximation. So sine θ1 becomes θ1, sine θ2 becomes θ2. So the equation becomes n1 θ1 equals n2 θ2. Second, we relate the heights. Heights are the same because it's at the same point. So x1 prime equals x1. Okay. So we save the height here, equation here, because nothing else to do. x1 equals x1 prime. However, we need to work a little bit more with the angle equation because these θ1 and θ2 are angles which I just added to the problem. They are not related till now with the angles that are given to us, like alpha naught, alpha 1, etc. So we have to relate the theta angles with the alpha angles, right? So how do we do that? So what I do over here is, so remember, if you look at this region where I'm pointing with the cursor, I have drawn the angle A. So θ2 equals A plus alpha 1 prime. So I have to figure out how to relate alpha 1 prime with θ1, right? So alpha 1 prime equals θ2 minus A. Okay. Next, we use the arc length relationship. So now we have to figure out what A is, because I just added another angle to the picture, A. So what is A? Can I relate it in some way to the terms that I know? Yes, I can. How? Remember the arc length relationship that I first discussed. So S equals R theta. So in this case, this height H or S or x1 prime in our case equals the radius length R times the angle A. Again, because these alternate angles are equal, so this line is parallel to the optical axis, so this angle A is also equal to this angle A. So x1 prime equals R times the angle A. So we are working toward a relationship here. So use arc length relationship to get x1 prime equals R times A. So A now we can figure out is equal to x1 prime divided by R. And finally, we go back to this equation and replace A, and we get x1 prime over R. So alpha 1 prime equals θ2 minus x1 prime over R. Okay, so we save that equation over here and then work and go forward. So now we have the Snell's law equation, which was here, n1 θ1 equals n2 θ2, and an alpha 1 prime equation over here. So these are summarized in here, and we combine these two equations, basically replace θ2 from the above equation. So θ2 equals n1 over n2 times θ1. So I replace that n1 over n2 times θ1 minus the second term x1 prime over R. We are almost there. So we just need to replace θ1 with some angles which are alpha, and we should be good to go. So how do we do that? So now look in this place where I'm pointing with the cursor. And basically I've saved the arc length equation over here where I'm saving my equations for later use. So over here, I extend this parallel line to the optical axis toward the left. And I define another new angle, B, over here. Oops, B over here. So alpha naught was defined over here. Again, alternate angle rule. This angle is also alpha naught. So we have alpha naught, B, and we have theta 1. So what is theta 1? Theta 1 is B plus alpha naught. So we are almost getting there. Now concentrate on these two regions, right? So we are going to use the opposite angle. So this line, which is the radius, and the optical axis, they intersect each other. So these opposite angles, which is B and A, are also equal to each other. So B equals A. So in this equation, alpha 1 prime, I rewrite it over here, replace theta 1 by B plus alpha naught, like so. Everything else remains the same. And then replace B by A. So everything else is here, remaining the same, just B got replaced by A. And from above, where I was saving equations, I have alpha 1 equals alpha naught. So I replace alpha naught by alpha 1. So summarizing, I've just same equation which is here, I've written over here. Alpha 1 prime has now been related to alpha 1, which was the angle at which the ray was coming in, and the alpha 1 prime was the angle at which the ray was going out, right? Oh, sorry. So also I replaced A with x1 prime over r, the arc length relationship. So all the extra angles that I introduced, like theta 1, theta 2, A, and B, have now been completely substituted by terms which we know, like x1 prime, n1, n2, alpha 1, and radius of curvature. So alpha 1 prime, the exit angle equals n1 over n2 times this term, which has x1 prime and r from the arc length relationship, alpha 1, because alpha 1 equals alpha naught. And again, the second term from the arc length relationship, from this relationship. Okay. So finally, we have a good form. So I just rearranged the terms like to make them look like a proper equation over here. So I can relate my alpha 1 prime with alpha 1 using n1, n2, and r. So just simplification, nothing else. And you can just work this out by yourself. It will be helpful for you. So, and the slides will be provided. So you can just redo the math by hand, I would suggest. Okay, so this is the refraction at spherical surface equation. Free space propagation equations were here, the height and the angle, refraction height and angle, done. So I saved this over here. So I ran out of space, so I basically moved everything down here. Okay, so next we have to do free space propagation in glass. It will be exactly the same as the previous time, just to replace the values with the new values. So you had x1 equals x naught plus alpha naught times d01. You have x2, in this case, this height. Oops. In this case, this height x2 equals x1 prime, this height, plus this extra height, which is equal to alpha 1 prime times d12, the distance propagated along the optical axis. And angle doesn't change, so alpha 2, the exit angle, would be equal to alpha 1 prime. I should actually draw the alpha 2, which is basically extending this and drawing another angle. I'll do that before I share the slides. So that's your final angle, right? So to summarize, the three phenomenon that took place: free space propagation in air, refraction at spherical surface, free space propagation in glass, all the geometry that we worked out over here, and all the three set of equations that we made, right? Are here. So these are for general media, like I said. For specific media like air and glass, just replace the values of n1 and n2 and so on. So we have all these sets of equations. The final thing which remains is to equate x2 with x1, x2 with x naught, and alpha 2 with alpha naught. So I didn't work that out here, but it's pretty straightforward. Just start with this equation, start with the third equation, replace x1 prime from the second equation, replace alpha 1 prime from the second equation, replace alpha 1 from the first equation. So all the terms will just get substituted, and you will have your final equation. You'll have your final equation equating x2, the final height, with x naught, the first height, and all other terms which are known to us. And alpha 2, again, I'll draw this alpha 2, which is basically just extending this here, alpha 2 with alpha naught and x naught. So these two equations are very important for us to remember in analyzing these optical systems. So we have basically covered up till here, where these equations are given. So the math wasn't worked out here. So I've added these slides to work out the math, and you can redo it by yourself later on. So again, 3 sets of equations are also provided over here. Propagation through distance 0, 1 is what I termed as free space propagation in air. Refraction at spherical surface. So again, first set, second set, and again, second propagation, so third set. Over here, I also pointed out my first set, second set, third set, and putting them together is this equation. Putting them together is this equation. Notice there is a typo in the PDF, so this R should not be there. So I will correct that before I post it. So this R is not there, basically. That's a mistake in the PDF. Okay, any questions about the math? No. Yeah, just work it out once by yourself. And if you have any questions, post on Slack. Since I managed to finally get on there last night, I'll respond to them. I think it's pretty straightforward. You just have to remember your geometry, trigonometry, all these identities, relationships, and so on. And that's it. Okay, so next slide talks about some sign conventions that are used when solving these problems. Just some things to keep in mind for when you are asked to solve problems. For like, this slide is very important for the midterm, right? So if in the midterm you're asked to solve some problems, and if you mess up the sign conventions, ultimately your answer is not going to be correct. So always refer to this slide.
So will those information be included in the exam, or
Sorry, which one?
the former information, the reflection, all those things, will they be included in the exam?
Yeah, I think up to September or whatever date, I think October, some date Dr. Menon mentioned, that is in the midterm. So all these math is in the midterm. But we'll see that you won't have to work out the geometry, because we'll learn something else in the second part of the geometric optics lecture called the matrix formulations. Actually, you have to stress more on that. So this is like the background math that I discussed. You will not be asked to derive this, let's say. But
yeah, so
there are more interesting problems that we will work out.
Yeah, that's a good way to say it, Apratham. You're absolutely right. Let me make 2 important points about the midterm. First of all, you don't have to memorize anything. All the exams that I have in this class are open book, open internet. And of course, it's an honor code that you don't communicate with anybody. Again, the goal is for you to learn. The most important thing is to gain intuition. So the math is important for you to work out. So definitely you need to work out, but you need to understand what it is that you're working out. Okay. And the exam will really focus on that part of it. The other thing I want to make it very clear is that even if your final answer is incorrect, you will still get points if your approach is correct. So this is, again, in my mind, the approach is much more important. How you approach the problem, how you try to solve the problem, is much more important than that final answer.
Thanks for the information. And sorry, I forgot about it. Last time you mentioned, I think you said final was option no for like one of the session. Which session was that?
Section 90, the online students.
090.
Oh, okay, cool. Yes, thanks.
And also I should, as I mentioned at the beginning, everything up to the midterm review, which I believe is October 13th, is included in the, will be included in the midterm.
Okay, cool. Thanks.
Yeah, so like Dr. Menon mentioned that if you will have access to the slides. So, and I will also do the midterm review. I'm doing the midterm review as well. So I'll go over these again once. So sign convention slide is very important. So when you solve your geometric optics problem, and there will be one, don't forget this slide, basically. So what it says is light travels from left to right is convention. And if light travels from left to right, the radius of curvature is positive when surface is convex, like bend like this, convex toward the left. Longitudinal distances are positive if pointing to the right, and lateral distances are positive when pointing up. And the ray angles are positive pointing in the counterclockwise direction. Just keep these values in mind. So when you plug in the radius of curvature, if the surface is concave, like it's bent the other way, make sure you put a negative sign in front and so on. Okay, so now this is a special case for on-axis image formation. So what we discussed till here was the very general situation, right? Everything is included, like general ray, general propagation in free space, general lens, general image formation. So now we look at a special case of on-axis image formation. So what you have is a point on the optical axis from which a ray is going out. It is suffering refraction at the interface between the two media, and it is bending inward to form an image P of the point object S on the optical axis. So how are you going to solve this equation? Like what relationships can we derive from this? So we'll just, this is how you put the equations into use basically. So we'll just resort to these general equations and analyze the special case and plug in some values. So one thing we can directly see in the general equation, the ray had a height above the optical axis. In the special case, there is no height, so x0 equals 0. And all rays, irrespective of which angles they are going out, have to be collected to the point P, irrespective of the angle, to form an image, right? Which means that this second term can be set to 0. There shouldn't be any angle dependence for the image to form. So if we set all this term to 0 and solve the equation, we basically get this. So I've done that over here as well. You can follow the math. So just I've reproduced the drawing over here, written my equations. I've written that here x0 equals x2 equals 0, and all rays must reach P, which means this second term in the first equation can be set to 0. Then I've done some simple math, like multiplied by n1, n2, and d1, d01, d02, and so on, and basically simplified the equation to get this. So n2, or in this case n prime, over d12 plus n1, in this case n, over d01 equals n2 minus n1, that is n prime minus n, over r, which is the radius of curvature of the spherical surface. So same over here, and same equation that I derived. Why this equation is important is because this is also the imaging equation, as we will see later on. And this right-hand side defines the power of the spherical surface. The units of the power is diopters, or inverse of length, so 1 over meter. Next is another special case where you have light rays coming from infinity, parallel rays coming from infinity, like suppose light rays from the sun coming toward the earth can be assumed to be parallel rays because the distance is so large. So image of point object at infinity. So very far away you have an object, all rays are coming in parallel. What happens to your equations? Again, you can work these out by yourself. I have also worked out the math. Just do it, tally with the whatever I solved and double check. And so I have my set of equations. Here I write x2 again becomes 0 because all the rays come to a focus at a point. And alpha naught equals alpha 1 equals 0, right? Because all the lines are parallel to the optical axis. So no angle is subtended by the incident rays. So those angles are 0. So I plug those into these equations and I solve for d12, which is this distance, is given by minus n prime over r or n2r, not over r, minus n2r or n prime r over n1 minus n2. So this d12 is also defined as the focal length of the lens. How do we define the focal length of the lens? If we have parallel rays coming in, all the parallel rays will always be focused at the focal plane of the lens or the focal length away from this interface. This is also what was shown in the animation, by the way. So in the animation, these rays are parallel rays. We might look, if you look carefully, all these are straight lines. So these are parallel rays coming in, and that's exactly how I drew the arrows. The arrows are horizontally parallel to each other. And you see what happens is the arrows show the bending, and you can see how the waves are also bent and they come to a focus. So see, it's getting smaller in size, and roughly here is where the focus is. So this is the focus of the lens. So all the parallel rays are focused at this point. And the light energy is also being concentrated because the energy which was spread out over this large area is being concentrated to this small area as well. So this is the wave optics animation of this problem, that this special case problem, parallel rays going in this problem. The animation is exactly what is shown over here. Okay, so this is point object imaged at infinity, just the reverse. I think I'll leave this up. You can take a look at what this is, what this case is, and solve the problem by yourself. And if you have questions, ask me later on. Okay, so I think I have about 10 minutes. I'm not sure if I want to start the matrix formulation right now. The class ends at 1:45, right? So yeah, maybe I think I can.
Yeah, I think we should stop because that's a lot of material and I don't want to overwhelm.
Yeah, because that's also a new thing. So let's do this in the next class. Just
on Thursday.
yeah, go over the math for the time being that we discussed. Yeah.
So as Apratim mentioned, it's important you can go back and watch the video and certainly do that, but certainly try to work out the math yourself of the basic concepts. This is quite important. In the exam, of course, we won't ask you to derive any of the stuff, but for the purposes of understanding, I would like you to do it yourself by hand. And again, if you go work at Facebook or Google or Amazon, you will never do this by hand. You will use fairly sophisticated software to do this, as you will learn during this class. But it is very, treating a piece of software as a black box is an extremely bad idea. You need to really have a feeling for what it is doing. Because if it gives you unphysical solutions, which it can many times, you need to be able to know it. And this is an important skill. So in the interest of not overwhelming you, I'd like to stop the class a little early today, but let's see if there are any questions first. Okay, and that's fine. You will have questions, by the way, and it's okay to have questions because these things are not necessarily simple. So just post them on Slack, and again, just email me or Apratim. Okay, so we will stop here. Again, let me remind you to contact your teammates and All the notes will be posted today. Give us a few hours. Typically, everything will be posted the lecture before the lecture. Worst case, it'll be the same day as the lecture. Okay, I don't have anything else. So let's adjourn now. And yeah, good luck. And hopefully you can gain some intuition from the concepts that were discussed today. Great. Thank you, Apratim.
Thanks.
Thank you, everyone. Take care. We'll see you all on Thursday.
Thank you.